I welcome you to the second part of Elitzur-Vaidman bump detection algorithm. In the previous video, I have defined the problem and have given two naive solutions of the problem. In this video, I will build upon those solutions and present a solution which is near perfect. Before starting the solution, let's cover some background material. So, background. Number 1, ket 0 and ket 1 are orthogonal with each other. It implies that there is a 90-degree angle between them. We can verify this by doing our inner product of ket 0 and ket 1, and our answer will be equals to 0. Thus proving that ket 0 and ket 1 are indeed orthogonal with each other. Secondly, ket 0 and ket 1 are on the unit circle. We can verify this by taking the norm of ket 0, which will be equals to the norm of ket 1, and that will be equals to 1. Therefore, ket 0 and ket 1 are on the unit circle. Secondly, R theta is a unitary matrix. R theta is a matrix that can rotate two-dimensional objects. It is equals to cos theta minus sine theta, and cos theta. It rotates qubits by angle of theta, and if theta is positive, then we have anti-clockwise rotation, and if theta is negative, then we have clockwise rotation. We can verify that R theta is indeed a unitary matrix, and we can make quantum gates using R theta by taking conjugate transpose of R theta and multiplying it with R theta, and our answer will be equals to identity. Thus, it is indeed a unitary matrix. So the background number 3. So we can write ket 0 also as equals to cos 0 times ket 0 plus sine 0 times ket 1, and our answer will be equals to ket 0, because cos 0 is equals to 1 and sine 0 is equals to 0. So if we rotate ket 0 by an angle theta, then this distance represents sine theta, and this distance represents cos theta. If we are near to ket 0, then cos theta will be longer as compared to sine theta, and this new qubit, this new point, will be equals to cos theta ket 0 plus sine theta ket 1. So if we measure this new point, then probability of cat 0 after measurement will be equals to cos theta square, and probability of cat 1 after measurement will be equals to sin theta square. And if we are near to 0, then probability of 0 will be much greater as compared to probability of 1. So what I'm saying is that for small theta, cos theta square is greater than as compared to sin theta square. And we also know that sin theta is approximately equals to theta for small thetas, and cos theta is approximately equals to 1 minus theta square over 2 for small thetas. Therefore, when we are near cat 0, then and we have moved by a small angle theta, then if we measure the new position of our qubit, then we will get cat 0 with much higher probability as compared to cat 1. So after this background, let's do the main algorithm. So let's see the quantum circuit that solves Elitzur and Vaidman bump detection problem to near perfection. We start with cat 0, and then we give cat 0 to a unitary gate that rotates cat 0 by an angle pi by 2n. Then this rotated qubit is fed to a device, and that device could either be a working bump or a dud. The device has a measuring apparatus inside it, but in case of dud, this apparatus is not working. Otherwise, this apparatus measures the input qubit. The output of the device is then fed back to the rotation gate, and we continue these iterations for n times. After n times, we measure the outcome and print it. Now let's see the outcome of this circuit at different stages. We call this stage 1. So the outcome of this stage will be cat psi 1. We call this stage 2, and outcome of this stage will be cat psi 2. This is stage 3, and outcome will be cat psi 3, and this is our final stage, and outcome is cat psi 4. So we start with the case where the device is a dud. In case of dud, cat psi 1 will be equals to cat 0. Now we have rotated cat psi 1 by an angle pi by 2n. Therefore, cat psi 2 will be equals to cos pi by 2n cat 0 plus sin pi by 2n cat 1. And cat psi 2 will be fed to the device, and because this device is a dud, therefore it will not measure the input. So cat psi 3 will be equals to cat psi 2. Cat psi 3 will be same as cat psi 2. and then the ket psi 3 will be given back to the rotation unitary matrix and will be rotated once again. So we are done with our first iteration. This was our first iteration. In the second iteration, ket psi 2 will be equals to cos 2 pi by 2n ket 0 plus sine 2 pi by 2n ket 1, and ket psi 3 will be equals to ket psi 2, and ket psi 3 will once again be given as input to the rotation circuit. So in this way, our kth iteration will be that ket psi 2 will be equals to cos k pi by 2n ket 0 plus sine k pi by 2n ket 1, and our nth iteration will be that ket psi 2 will be equals to cos pi by 2 cos pi by 2, because there will be n here and n will cancel with each other, so it will be cos pi by 2 ket 0 plus sine pi by 2 ket 1, and the outcome of the nth iteration for ket psi 2 will be equals to ket 1, because cos 90 is 0 and sine 90 is equals to 1. Therefore, ket psi 2 will be equals to ket 1. Now, ket psi 2 will be fed to the device and came out unchanged, and we will have ket psi 3 equals to ket psi 2, and this time we will not iterate any further. We will get out of these iterations. So ket psi 4 will also be equals to ket psi 1. We will measure, and our outcome will equals to 1. So in case of dud, we get ket psi 1 with 1 probability, that we will always get our outcome as psi 1 for dud. So now let's see what will happen if the device is a working bomb. So if the device was a dud, then the output of our circuit will always be equals to ket 1 with 1 probability. And now let's see if the device is a working bomb. Then ket psi 1 will be equals to ket 0. Now we are starting with the first iteration. So this is our first iteration. In the first iteration, ket psi 2 will be equals to rotation of ket psi 1 by the angle pi by 2n, which is equals to cos pi by 2n ket 0 plus sine pi by 2n ket 1. Now ket psi 2 will be fed to the device, and in this case, because the device is a working bomb, so the measuring operators inside the device will measure the input. So after measurement, we have two choices. One choice is that by probability of sine pi by 2n whole square, we measure cats 1, and in this case the device explodes and we all die. However, if the angle pi by 2n is very small, that means our n is very large, then we can drastically reduce the probability of explosion. With a very small probability, we will be exploding, but with a very large probability, our output will be cat 0 instead of cat 1. So with probability of cos pi by 2n whole square, our outcome will be equals to cat 0, and we will live to see another day. So after measuring, we will get to the cat psi 3 or will explode, and the cat psi 3 will be equals to cat 0. So the second iteration will be exactly the same, because the input of first iteration was cat 0 and we get the output of first iteration was cat 0. Therefore, second iteration will produce output of cat 0. So the result of the second iteration, that is cat psi 3 after the second iteration, will also be equals to cat 0, or we will explode with some small probability. Similarly, after n iterations, our outcome of cat psi 3 will be equals to cat 0. Therefore, cat psi 4 will also be equals to cat 0, and the output of the circuit in case of bomb will be equals to cat 0. So in case of bomb, we will always get cat 0 or we will explode. So now let's summarize this whole algorithm. So graphical summary. In case of dud, after first iteration, our cat 0 will be rotated by an angle pi by 2n. So we will be here after first iteration at cos pi by 2n cat 0 plus sine pi by 2n cat 1. And because our device is not measuring this input, therefore cat 3 will be same as cat 2, and we will fed cat 3 back to the rotational unitary matrix, and for the second iteration we will get here, we will get cos pi by 2 pi by 2 n cat 0 plus sine 2 pi by 2 n cat 1. So similarly, at the kth iteration, we will get, in case of dud, cos k pi by 2n cat 0 plus sine k pi by 2n ket1. And after nth iterations, we will be at ket1. So this was our ket0. And after n iteration, we will be at ket1, because ket1 is equals to cos pi by 2 ket0 plus sine pi by 2 ket1. So in case of dud, we will always measure ket1 at the end. So our output will always be ket1. So our outcome of the circuit will always be equals to ket1 in case of dud. In contrast to that, in case of bump, the first iteration will be exactly the same until ket psi 2. So at ket psi 2, we will be same as ket psi 2 in case of dud. So we will have a rotation of cos pi by 2 n ket0 plus sine pi by 2 n ket1. This is our ket0, this is our ket1. So we have rotated by a slight angle towards ket1. But then this result will be measured, because in case of bump, our measuring apparatus is working. And after measurement, either we will explode with the square of this probability, we will explode with the square of sine pi by 2 n square, or we will get 0 with the square of this. And when we get 0, then that means that for the second iteration, we will once again be at ket0. So for each iteration, we will go up, and after measurement, we will go back down. And if unless we explode, that means we will remain at ket0 or we will explode. Outcome of our circuit in case of bump will always be equals to ket0. So in this case of bump, our outcome is equals to ket0. In case of dud, our outcome is equals to ket1. But now one thing remains to be clear, that with what probability we will explode and with what probability we will get ket0. So now let's clear the board and calculate the probability. So probability of no explosion is equals to probability that we don't explode after the first iteration. So no explosion after the first iteration times probability that we not explode after the second iteration, no explosion after the second iteration times probability that we don't explode after the nth iteration. Probability of no explosion is equals to that we don't explode in any of the iterations. And basically we are using this formula, that probability of A intersection B intersection C is equals to probability of A dot probability of B given A dot probability of C given A intersection B. However, when A, B and C are independent, then probability of A intersection B intersection C is equals to probability of A times probability of B times probability of C. And in this case, they are independent because every time the input of the circuit is ket0, so we will get the same probability of explosion every time. Probability of not explosion for the first iteration is equals to cos pi by 2n whole square. Probability of no explosion in the second iteration is cos pi by 2n whole square. And similarly, probability of no explosion at the nth iteration is pi by 2n whole square. And they are equals to cos pi by 2n here. So 2n here. So that's the probability of not explosion and getting 0 as an outcome. So now let's see what is the probability of explosion for different n's. So we have here n, and here we have probability of no explosion and detecting bomb or getting outcome of get 0. So detecting bomb with outcome of get 0. So in case where we have only 2 iterations, the n is equal to 2, we detect bomb with the probability of 50%. So we explode with the probability of 50%, and with the probability of 50%, we successfully detect the bomb. In case n is 10, then with a probability of 94%, we detect the bomb successfully. So we explode only with the probability of 6%, but with the probability of 94%, we detect the bomb. How are we getting this probability is by putting n is equal to 10 here. So this thing is calculated with this formula, that cos 20 pi over 20, and this should be equals to around 94%. Similarly, for 20 iterations, we are able to detect bomb successfully without explosion with the probability of 97%. And with 50 iterations, that means when n is 50, we are able to detect bomb without explosion with the probability of 99.99%. And with 500, n is equal to 500, we are able to detect the bomb without explosion with the probability of almost equals to 1. So it is because it is so many 9s that calculators round up to 1 in case of 500. So it's almost equals to 1. So I hope that you are able to understand this beautiful algorithm of bomb detection, and you will be able to appreciate its beauty. See you next time. Stay tuned.